All right. Good morning, everyone. As I was introduced, my name is Ganesh Patil. I'm a postdoctoral research fellow in Mechanical Engineering Department. Is this fine? Yeah. Okay. I'm a postdoctoral research fellow in Mechanical Engineering Department as well as an affiliate with Midas. So I would like to begin this vision talk with a simple thought experiment. Imagine if machines could see using sound. Now, if we close our eyes for a moment, the world around us feels incomplete. And this is because we humans are visual creatures. We build maps, we navigate, make decisions, largely based on what our eyes tells us. But in nature, vision is just one way of understanding our world. If a bat or a dolphin close their eyes, the world hardly changes for them. This is because these animals listen to see. And this is the question that drives our research. Can we make machines to do the same? That is, to see using sound. So we are motivated by nature's two great masters of acoustic perception, bats and dolphins. What these animals do is they employ biological sonar or biosonar in order to do a specific task known as echolocation. So what these animals basically do is they generate high-frequency sound pulses at frequencies higher than human hearing. And then they listen to the echoes that bounce back from nearby objects. By interpreting these echoes, they construct a detailed mental picture of their surrounding. And this is true no matter whether we talk about air or water. Bats fly at full speed through dense forest, even at night, without hitting a single branch. Similarly, dolphins navigate underwater, deep underwater, where sunlight never reaches, still managing to avoid rocks, caves, and even each other effortlessly. And what's remarkable here is that these animals don't rely on huge data sets. They don't train on years of labeled examples. Rather, they learn adaptively. They refine their perception through their experiences. And there have been studies that showed that these animals can recognize the size, shape, material, texture, and even motion of the surrounding objects purely using sound. And if you consider all this together, you will realize that this is not just detection. This is an intelligent interpretation. And that's the puzzle that we haven't been able to solve so far. So on one end, we understand the physics of sound. We know how it travels from one point to another, how it reflects, how it scatters. What we don't understand is the intelligence behind how do these animals use sound. How is the information about the surrounding encoded in those echoes? How do their brains interpret it? And how do they adapt as their environment changes? All these are open questions. And what we think is the acoustic cognitive skills of these animals is the central part here. So yes, sound is a fantastic way to gather information about our surrounding because it contains different frequencies which interact with different objects differently. So there is a lot of rich information that these animals is receiving when they listen to an echo. But then they have highly sophisticated cognitive skills, highly evolved cognitive skills that enable them to interpret these echoes to extract meaningful information. So these animals can extract various acoustic structures, things such as different spectral, spatial, or temporal patterns within those echoes. They can categorize different sounds. They can also consider this, they can also do this while keeping in mind the context, meaning the dolphins, for example, can interpret echoes irrespective of whether it is in an ocean, in a river, or in an indoor pool. And based on this interpretation, they change their acoustic behavior and accordingly perceive. So if we want the machines to use sound intelligently, we don't just need a better sonar, we need perception models that learn just like these biological organisms learn. And therefore, the central question here is, how can we teach machines not just to detect, but to learn, adapt, and reason based on the available acoustic information? Meaning, if a machine captures an echo, can it extract meaningful information? If it can't, how should it change its acoustic strategy to gather meaningful data? Or maybe it can extract some information, but it's not enough to make a specific decision. So in that case, how should it adapt its strategy to bridge that gap? And we think that artificial intelligence is the connection here. Artificial intelligence gives us this ability to extract subtle features from these complex ecos, and it can help us interpret just like the way these cognitive skills make these animals do this perception. And that is the foundation of our research vision, which is we want to transform the way engineering system perceives by, number one, we want to learn from Biosonar, so we can take some notes from how biology does it, and then mimic it using these AI-driven models. Now, you might wonder, why do we need to transform the perception this way? And the reason for that is a whole world of possibilities opens up if machines could perceive using sound. Imagine a fire rescue drone operating in a dense smoke where cameras can't see, or a wearable device guiding a visually impaired person safely through a city street. So in these situations, sound can provide awareness where vision fails. Similarly, think about environments we can't reach. Deep sea ecosystem where radio and light waves vanish, or planetary surfaces where GPS isn't available. These AI-driven biosonars can give us this ability to map, navigate, and even learn these extreme environments in a complete darkness, potentially opening new frontiers in ocean science and space exploration. And we also know that sound gives us this ability to probe what's there beneath the surface. In medical field, it is used for diagnosis. In engineering, it could be used to identify microscale cracks, for example, in aircraft structures or bridges, way before they fail. And if you look all these possibilities together, I'm sure you would agree that this sound-based perception is not just an alternative to vision, but it's a new way to understand our world, from saving lives to exploring the unknown to even seeing what's been invisible. So with this research vision, we are particularly focusing on dolphins. And one of the questions that we are asking is, can we understand how do dolphins learn objects that are unfamiliar to them purely using sound? And if we can understand that, can we mimic that? Can we replicate that artificially? And for that, we are working on a very interesting but controlled echolocation experiment. So does that mean 1 minute is remaining? Okay. It will take a little bit more than that, but I'll try to finish it. So, what we do here is we cover the dolphin's eyes with soft eye cups. So this basically blocks their vision, making them rely purely on sound waves. And then the experiment has two parts. There is pool A and pool B. So we drop an object in pool A. The dolphin's job is to echolocate, meaning generate sound, receive echoes, and learn that object. Then he swims over to pool B, where we present him 3 objects, one of which is the same as in pool A. So what he does is he again echolocates, learns these 3 objects, and then chooses the one that he thinks best matches with the object in pool A. If he does the correct matching, he gets a fish as a reward. So we do this particular experiment because we can see how the dolphin is behaving, and we can also gather the acoustic data so that we can analyze the biological process. But on a broader picture, what we ultimately want to do is, number one, we understand how do they adapt their behavior, so we can use that in order to develop our artificial system. And then we want to develop an AI-driven perception model that takes these echoes, this sound as an input, and then tells us what could be the object from which they are generated. And ultimately, we want to couple them so that we can replicate this biological echolocation, but in an artificial manner. Now, we made some observation during this experiment, and I'll quickly go through this, which is that these dolphins don't require a lot of data to learn. Maybe around 100 to 200 echoes are enough for them to understand this specific object. So they learn much quickly. They also learn these objects sequentially, so one after another, without needing to go back or revisiting the one that they have already learned. But if you want to replicate this, we certainly want to train our models to mimic this behavior, but gathering physical echoes from actual experiment is not an easy task. And therefore, how can we train these models synthetically by using simulated data, but still generalize them to measured echos is what going to be the challenge. So we have made some progress, and I will skip that for now, but I just want to let you know that we can develop models where we can train these networks with a very limited data, just like mimicking the efficiency. We can make sure that the data is learned sequentially, so we don't have to learn previously learned object. We can only focus on the new objects. And we can also train these models synthetically and still make sure that they work on the measured echos, because we know the physics between the simulation and the actual experiment. And there have been some interesting behaviors that we can learn from these dolphins when we do those experiments. And perhaps I can talk with you for those who are interested throughout the day. And I will just quickly point out that this is just the starting. There are so many challenges and steps that we have to go through in order to achieve this final objective of making the engineering machines to see using sound. For example, we have to develop a coupled system where we let the machines choose on their own how they should listen or how they should gather data based on what they have already learned. We have to make sure that these acoustic AI models are interpretable, because then it can also help us understand what is the cognitive process that happens inside those animals when they interpret these echos. We have to extend this for all the complex objects that we have in our real world, which can be irregular and composite. And finally, we also have to consider the fact that the real world is basically a cluttered environment, which has so many overlapping echoes and noises. So how do we make machines to disentangle those effects and only focus on the most important one? And all of these things cannot be possible in isolation. It will take people from biologists to acousticians like me, to robotics people, to experts in signal processing, and of course, there is AI researchers. So with that, I would just like to acknowledge different funding agency and a group of interdisciplinary team which is working on this research project, and I'm happy to take your questions if there is a time. Thank you.
Thank you so much. So we have time for one question here. How do you manage noisy environments like factory settings? How can this work there?
So we ideally would want this to work there. If we know what is the characteristic of noise, we could train our models with that. I guess that's a straightforward answer. But the other reason is we could also try to minimize the noise itself. So there are different ways we could handle that problem.
Okay, yeah. Thank you. And then maybe one more question here. So I'm a linguist, actually. This is actually relevant to me. What is the relationship between how dolphins use sound and how humans use sound?
Yeah, so we use sound generally, I would say, to localize the source, meaning what I would be interested in is knowing from where the sound is coming from. But what these animals do is they also want to learn more about it, not just from where it came from, but what is that thing? Is it a solid object? Is it a flexible object? How big or small is it? Is it moving or stationary? So I think it's much more intelligent and detailed than what I think we do it.
Okay, thank you so much. I really appreciate that.
Thank you.
All right. Thank you. A little bit of a mouthful, but bear with me here. So thank you to the Midas staff, the program committee for making this happen. It's going to be a really exciting couple days here. And yeah, it's a pleasure to be here to talk to you today a little bit of my work at the intersection of differentiable science and astrophysics. And I'll be talking about some of the case study where we're using this to enhance our science. So here's the takeaway. So I think one of the things we're all interested here is how ML and AI will push the scientific frontier. And a lot of this will involve deep learning, but I'm here to advocate for a kind of a hybrid approach where we're also going to be utilizing a lot of the associated hardware, software, and infrastructure as a rising tide that lifts all boats. And I think the promise of transformational breakthroughs is really going to be found at this intersection of physics-based models and data-driven AI models. And some of the programming paradigms that we're talking about today is going to be what's living at that intersection. Okay, so to take a step back, we're probably all familiar that there are three main things that have driven this incredible AI revolution over the past 10 years: data, compute, and algorithms. I'm going to skip over data for the sake of time and focus on compute and algorithms. So what I'm showing you here is the total amount of compute power that's gone into training state-of-the-art models at the time. You can see a very sharp rise in this total compute power over the past 10, 15 years. And this is really a product of a couple of things. One, the transition to very high-performance graphics processing unit power for training these models, the cost and accessibility of getting those GPUs, and then parallelization, where we can now kind of extend Moore's law by parallelizing over 10, hundreds, thousands of GPUs to train these models. And I think one of the things we're interested in as a scientific community is how to leverage this uptick in computing power for science. And the next is algorithms, right? So these days, you'd be hard-pressed to find a research field, whether it's language, vision, or audio, where a neural model is not the state-of-the-art. But there's another somewhat underappreciated aspect of the algorithmic development of AI, which is something known as automatic differentiation, or autodiff. This is really the train that's powering the AI revolution if data and compute is the fuel. And what this allows you to do is to take any kind of black box model that you can code and compute gradients of a loss function with respect to those model parameters. It's distinct from numerical methods in that it's exact, and it's distinct from symbolic methods in that it's highly scalable. And this is really what allows us to update the model parameters for our billion, tens of billion AI models. But it's also applicable to physics and science. So one of the emerging paradigms is something known as differentiable programming, where we take these same software tools and we write our physics simulations in a differentiable way. You can do this directly, which is what I'll be talking about today, or you can develop neural network emulators to help speed this process and make simulations that perhaps weren't differentiable. And the power of gradient-based descent and sampling routines is really what opens this Pandora box for pushing scientific inference to new frontiers. Okay, so again, taking a step back, I think what we're all interested in here is understanding, as Andy was getting at earlier today, how will AI be widely adopted in the scientific community? I think it's clear that we're in the ML and AI for science era. You can look no further than the Nobel Prizes in physics and chemistry last year. But I think we're going to ask the question is, how will this seed more widespread adoption? And there's, to put it crudely, I think two paradigms. One is we're going to stick these AI models in our extremely high stakes end-to-end kind of inference capabilities where we're giving it all the data we've ever taken from our telescopes, and it's going to spit out the equations of the universe and tell us about the fundamental parameters of the universe. But there's another model where these AI tools are really cushioned within existing approaches, either to help accelerate science or to move the needle on a particular sticky kind of bottleneck that limits science. And so what I'm showing you here on the right is a way that we're using AI to detect radio frequency interference for radio telescopes. And this is a big problem because it really limits the kind of science that we can do with our data. So having better ways to detect and remove this RFI allows us to use more of our data and to actually push the envelope in scientific discovery. And I'm not here to advocate for one or the other. I think what you're going to find is we're going to get transformational science out of both of these paradigms. And I think really the question is what tool is right for the right job? What's going to have widespread adoption within the scientific community? And what I'd like to argue here is that the kind of programming paradigm, differentiable programming, is really going to have a role to play in both of these. So it has a wide cross-section in the AI for science landscape. And I'll be focusing in on one particular kind of problem, which is inverse problems. Or if you have noisy, contaminated data, how do you infer the variables of a state that you'd like to estimate? And particularly these ultra-high fidelity inverse problems where you're at the frontier of some either resolution, data contamination, noise, sparsity. And what's interesting about these problems is that these are some of the most interesting problems, I think. They're also some of the hardest to solve. And in these cases, off-the-shelf models typically don't cut it. Right, so you're having to use some kind of domain knowledge to really push the envelope here. And some of the things that I've been working on specifically, and I'll talk about a little bit, is how can we use some of these differentiable programming paradigms to enhance this process, specifically on the idea of uncertainty quantification. And for those that are more technical, this is effectively trying to do joint posterior sampling across your entire parameter dimensionality. Right, and as Andy mentioned earlier today, uncertainty quantification is as important as your point estimate of the variable you're trying to estimate, right? It's really how we do science. And so if you have some data, for example, that you've taken on the right, as a scientist, we often fit trend lines, and you can do that. But just as interesting is what is the uncertainty about that trend line. And specifically, if you have a data model, which I'm showing on the left, the question is between the variables you'd like to estimate, which are in circles, the parameters you want to estimate, which are in circles, and the data Z, what is the uncertainty in your ability to infer those parameters? And specifically, if you have some kind of causal relationship between these parameters, if, for example, due to computational limits, you can't actually vary some of these parameters, what you're going to find is you're going to bias your inference. You're going to be overconfident in your uncertainty, and that's going to be a problem for your overall inference. And so what I've been doing is trying to use the kind of wave of GPU compute and differentiable programming to really more fully unlock our ability to explore the full uncertainty profile of our forward models. Okay, so I am kind of an experimental cosmologist, astrophysicist, and one of the really interesting things that's going on right now is our ability to probe the full growth of the universe over the full timescale of its evolution. So going back to Andy, he introduced this kind of cosmological standard model, which we're beginning to stress test, and this is largely propped up by measurements of the early universe, which are on the left. The current era is on the right. We can look all the way back to a couple 100,000 years after the Big Bang, and we have very pristinely measured the clustering of galaxies in the local universe on the right. What we have yet to do is to systematically chart the adolescence of the universe, right? So we have good measurements of our universe in its infancy and its adulthood, but the next generation of cosmology and astrophysics will really be, can we probe its adolescence? And one of the ways that I'm doing this is with radio telescopes that can measure neutral hydrogen. So neutral hydrogen is a great tracer of cosmology because it's everywhere in the universe. It's the most abundant element. And as a consequence, we can use this to take a brain scan, if you will, of the universe over the full course of its duration. And this is going to really unlock the next generation of cosmological discovery. However, there's some challenges with this kind of approach. One is that we're looking for an intrinsically fairly weak signal masqueraded by incredibly bright data contamination. And this data contamination comes from a variety of sources, including our own galaxy, which shines very bright in the radio. And all of this is then modulated by the response of our telescope, which we know to some degree, but it's always imperfect. And so this sets up this grand challenge signal separation problem that we're still really actively working on. And I spent a lot of my time during my PhD and postdoc working on a particular experiment called Hera, which is the premier American telescope doing this currently. Okay, and what I mentioned is what's difficult about this is the dynamic range between the contaminants and the signal, which is about 10 to the 5 or 100,000, right? So I asked ChatGPT, give me a kind of a layman's example of what this is like, and it came up with a really interesting example, which is, this is a room. I think we have about 100 people maybe, but imagine if we were all talking kind of at a normal voice, and we would like to detect the wing beat of a mosquito somewhere in this room. That's kind of the scale of what we're trying to do. And for any of you who do audio signal processing, there's this classic cocktail problem where you're trying to understand who's talking, when, and where. And this is kind of taking that to the next level of trying to detect a mosquito in this room. And actually, we've done quite well with traditional techniques. So we've gotten down, what I'm showing you here are the best null constraints on the signal. My work that I've done over the past couple of years is shown on these blue hexagons. And the kind of fiducial theory that we'd like to detect is about an order of magnitude away. So basically, we're at moth wing beat currently, and we'd like to get down to mosquito. And the question is, how are we going to get there? And then how are we going to build confidence in those detections? And this is kind of the focus of some of the focus of my recent work is developing the first end-to-end differentiable pipeline for radio cosmology. And to put it simply, we're kind of using, we're building forward models at the largest scale we've ever built them. We've never been able to solve this problem with traditional techniques, but with the advent of, I would say scientist-friendly autodiff and GPU computing, we can now take on an entirely new scale of inference problems that we've never even really dreamed of doing. And so what we're doing is basically we're parameterizing the signal, the contaminants, and the instrumental response all in one model and learning them jointly. So we're learning the universe, the instrument, and the contaminants in some unified way, using GPU compute and autodiff as an accelerant. And one of the things that's particularly tricky, as I mentioned, is this instrumental response, which we know well, but not at 1 part in 10 to the 5. And so what I'm showing you here is an electromagnetic simulation of that Hera dish, of the response. And if you do normal things like you slightly deform the dish or you move the feed, you end up with percent level changes in the response. And we'd really like to not only understand that, but to what we call marginalize over that, or to vary the uncertainty. And this sets up a very high-dimensional sampling problem, which is just an unsolved problem in the field of statistical inference. And I'll skip over this a little bit, but this is one of the kind of cross-cutting applications of this work is we've experimented with other ways to precondition the system. This is going to get a little more technical in the next couple of slides, to enable effective and scalable inference. And so this allows us to actually optimize this approaching million parameter dimensionality, highly efficiently with a multi-GPU cluster through the NSF. And so the big thing is that we can recover. So this is a slice through that beam profile that is highly uncertain. Black is the truth, and red is our draws from this posterior. We can really well recover the mean and then also the fluctuations about that mean. So this is giving us the uncertainty. We can also recover the signal. This is with mock data. So I've injected a signal, and I'm trying to recover that signal top and bottom. And the key point here that in the last couple minutes that I'll talk about is our ability to measure this uncertainty. And so on bottom here, you're seeing a simulation through this MCMC chain. And what you're seeing is fluctuations in the recovered map is directly correlated to our uncertainty in the instrument and our uncertainty in the contaminants. So for the first time, we're able to fully explore this joint parameter space between the signal we want and all of the systematics that we would rather not detect. And then this is kind of the sticking point here. So you can compress that signal into a signal amplitude. We call this a power spectrum. And what you're seeing here is the power spectrum that's been recovered by the inference divided by the known truth that I put in. Okay, so we want this to be basically at 1. It's going to have some fluctuations depending on the uncertainty of our recovery. So traditional techniques for uncertainty quantification is in blue. We know how to do thermal noise recovery very well. And you can see for a lot of this space, these data points agree with that blue curve. What we've been able to do for the first time is to really explore this full uncertainty profile, propagating in an end-to-end fashion our instrument and our data contaminants. And this has allowed us to better estimate the uncertainty on the left side of the region. And why this is important is that if you had used our previous uncertainty model and you would see deviations from 1 on the left side, you would say this is a detection of new physics, right? This is something exciting, which we might eventually get there. But it's really important that you have a proper uncertainty profile. And so now with this updated model, we're actually able to use this data. So before, we would have a heuristic that says we think that data on the left side of the plot we don't trust, and we would just remove it from our inference because we don't trust it, right? But that's kind of ad hoc. We want a more robust way of doing this. So now we can actually unlock more of the data, improve the sensitivity of our constraints, and also be more confident in its robustness. So this is being scaled up to work on real data now. As I mentioned, GPU acceleration is absolutely critical to making this work. And with the resources now available to the scientific community, A100s, H100s, possibly in the coming years B100s, it's really exciting to see how AI compute and algorithms are going to just push the frontier of what we can do with our inference. So I'm actually a little early, but I'll leave it there, and happy to take questions. Thank you.
Okay, so one question here is, given the faster run times that you mentioned, I think this was the very end of the talk,
Yeah.
How much are you saving? And I guess we're referring to, money, dollars, right? We're getting back to the topic that was mentioned earlier.
Yeah. So, I mean, compute gets cheaper every year. GPU compute becomes cheaper and more accessible. There is an interesting question, which is, can you just buy more CPUs and do the same thing? And I think the answer is largely no, because that's assuming that your CPU implementation has perfect scaling, and at some point, based on the limitations of the memory bandwidth, you will achieve a bottleneck. So just the fact that you just have intrinsically better performance with GPUs is a power. The second thing is, I talked about infrastructure at the beginning. I haven't really talked about that, but there's an incredibly large amount of infrastructure that's being built for training large AI models. There's incredible financial incentive to develop these tools by these companies that are developing them, and a lot of these things are open source. And so I think what you're finding is, the interest is in parallel GPU computing, and so that's really where you're going to see kind of major improvements, I think, on the AI side. And the question is, can we actually leverage this to do better science? I think the answer is yes, and so I think that's why there's a lot of excitement around GPU computing. So.
Mike Myers from Great Talk. How translational is your approach or your code in terms of radio instrumentation versus
Yeah.
versus the nature of the problem you're trying to solve, or kind of adolescent democracy?
Yeah, it's a great question. Thank you, Professor Myers. So I would say one of the cross-cutting applications I mentioned was how to perform high-dimensional scalable inference. That's a problem in astrophysics and chemistry and biology. In terms of the differentiableness of the forward model, it is very specific to radio tomography. It is applicable to what we call total power autocorrelation measurements. It's also applicable to interferometry, which is the case I was showing. You know, I think what you're going to find is the kind of lessons about how to get it to work in practice. I have spent a lot of time, you know, even showing here how to actually leverage the GPU computing as opposed to, you know, overcoming I/O bottlenecks with caching. That's going to be applicable to really any practical implementation within the sciences. So I hope this is one of the lessons that we can kind of begin to cross-fertilize to other domains as well. Yeah.
Okay, next question from Pigeonhole here. Are you looking at neuromorphic computing?
That's a good question. Do you want to define it?
Well, it has a couple of upvotes. You're the person who asked the question. Can you specify? Or we can move on to another question, which is, are there open source packages for automatic differentiation?
Yes, yeah. So I skipped over it, but I mean, it's all the ones that you've heard of: PyTorch, TensorFlow, JAX, right? These are the tools, and you know, back in the day, Theano and Julia, of course. You know, these are the tools really that, by many metrics, have actually enabled the deep learning revolution, right? Because, you know, scientist-friendly, researcher-friendly tools for doing this is what enabled widespread adoption. And so we're simply rewriting our physics simulation with these tools in mind.
Thank you so much. We have time for one more. Because technology in the computing sector is now reaching its peak, is due to Moore's law. What is the expected next step to increasing computational power?
Yeah, that's a great question. I'm not a computer scientist, but I'll tell you what I know. So, you know, GPU computing also has its own Moore's law. I know it's not doubling every year, but I think what you're finding, and this plot is kind of showing it, is you're going from smaller transistors to parallelization, right? And this is where you're reaping benefit is in total compute, right? It's not just that the chip itself is faster, but that you're able to utilize more chips at once. And part of this is also experimental design. Can you design inference techniques and models that themselves are parallelizable, right? This is one of the kind of breakthroughs of the transformer network is its massive parallelization. And that's what has, you know, led it to being applied on these extremely large data sets. So, yeah, I can't tell you much about the chip design, but there's certainly improvements in our ability to access raw compute through parallelization, which is a huge area right now. Yeah.
Actually, this graph. So it says 1.4 times per year. That's, I think, from the 1955 to like early 2000s.
Yeah.
This is the black text on top of those colored dots. I can't read it too well. What is it, 4.0 times?
Yes, it's 4 times per year. But this is not in the performance of a chip. This is in the total compute used to train a model. So again, this goes into how much the company or the institution is willing to purchase in terms of compute. So that is cost and accessibility. And then also its inherent parallelizability, right? So if I have 2 chips and I can run them simultaneously on the same problem, I've, in theory, doubled my performance. But you have to come up with an inference approach that is actually scalable in that manner, right? Yeah, thank you. Appreciate it.
Thanks so much. Thanks so much to everyone for being here and for the conference organizers. And also, briefly, also want to congratulate all the prior speakers on their really incredible technical work. I'm a minimally invasive surgery fellow at Michigan Medicine in the Department of Surgery. And I appreciate the time to be able to share my work. I've been fascinated for several years now and been studying how physicians can leverage AI to make better patient care decisions at the point of care. And so that's what I'll be talking about. But before I kind of delve into that topic, I actually wanted to start by telling you a story of one of my favorite stories of computer-aided decision-making. And this story actually comes from 1997, after Garry Kasparov, the chess grandmaster, lost to IBM's Deep Blue. After he lost that match, he became fascinated by how humans and computers can think together. And so he actually started teaching chess in new ways with the help of chess-playing computer algorithms. And in his studies, he noticed a very peculiar phenomenon emerge, which is that specifically he noticed a small group of weaker-rated chess players that were consistently beating stronger chess players. And specifically, he noticed that this small group of less skilled human chess players collaborating with the computer algorithm tended to win games against highly skilled human chess players that were collaborating with the exact same computer algorithm. And when he looked into this phenomenon, he noticed that the difference between these two groups was that the less skilled players had specific collaborative processes for how to interact with the computer's recommendations. And so, but in contrast, the more skilled players didn't have any process for interacting with the computer's recommendation. And one of his, as he described in one of his talks, and from the 2010s, he said that he noticed that there was a lot of friction between the skilled player's strong sense of intuition as to what the right next best step was versus the computer's recommendation. And that friction sort of altered their combined gameplay in what he described as very unpredictable and sometimes often harmful ways. And so that gave rise to what's now called Kasparov's law, which is the idea that a weaker human plus a computer algorithm collaborating via a strong, well-defined process will tend to outperform a stronger human collaborating with that same computer algorithm but without an interaction process. And so as you can imagine, that observation or that theory is very relevant to how decision-making algorithms should be used in clinical practice for making decisions about patient care. Now, the sort of guiding principle or the dogma for all of clinical AI up until now has been that these algorithms should augment humans or that an AI-equipped human is the superior decision-making paradigm compared to what either decision-making tool, human or algorithm, can do alone. But now that more and more algorithms are starting to be tested on real clinical scenarios, that narrative is starting to unravel a little bit. It actually turns out in studies over the past few years that delivering the best prediction to the human physician does not automatically translate into the best possible patient care decision. Now, to be fair, there is some evidence that physician-AI collaboration is very effective. This is a landmark Swedish mammography study from a couple of years ago showing that when AI and radiologists collaborate on diagnosing breast cancer from mammography, the AI-assisted approach leads to higher, more accurate identification of breast cancers compared to human radiologists alone, and also cuts the radiologist's workload almost in half. So there is some evidence that collaboration is still highly beneficial, but within the last year or so, there have been numerous examples emerging from the literature where algorithms have been studied in real-world clinical practice where that collaboration actually doesn't help. And so the highest profile example is a study from around this time last year. It's a study of large language models versus physician specialists in diagnosing complex cases. Now, when the AI worked independently to diagnose these complex cases, diagnose these very complicated patients, it achieved a 92% accuracy, whereas physicians collaborating with the AI assistants only achieved 76% accuracy. However, when the physician was working alone, their accuracy was 74%. So collaborating with the algorithm only increased their accuracy marginally by 2%, while the AI, unaided by the human, achieved remarkably higher diagnostic performance. This phenomenon has this is not an isolated study. This phenomenon has borne out in several other studies of chest X-ray reading, EKG reading, lots of other clinical scenarios. But I think this is probably the most highest profile of them. And the theme across all of these studies is that, again, giving AI, clinical decision support AI to human physicians does not change their performance, or sometimes maybe marginally improves it, but that AI unaided by the human tends to surpass what either can do alone. Now, I'm a surgeon, and so there are several examples of this from the world of surgery as well. This is one study that shows this same exact phenomenon where when you ask AI versus surgeons to predict what will happen to patients postoperatively as far as complications go, in most domains, the AI outperforms the human surgeon in predicting what will ultimately happen to the patient. But then when you give that prediction to the surgeon's performance in predicting complications doesn't actually change at all. And this is actually borne out in some of my own research as well, which not only shows that surgeon-AI collaboration does not outperform what the algorithm can do alone as far as predicting postoperative complications, but more specifically, that surgeons tend to disagree with the algorithm at increasing rates as patients get more sick and more complicated, which are exactly the very scenarios where they might actually stand to benefit from those algorithmic recommendations. And so there's a very common explanation for this phenomenon as it's emerged over the past few years, which is that, physicians aren't completely comfortable with using AI. They still doubt its utility. They fully don't understand how these algorithms work or what its weaknesses are, which I think is all true. But what I want to propose is that there's an added layer of complexity here, which is that even if we physicians did trust these algorithms, we don't yet fully understand how to incorporate their recommendations into our intuition or into our clinical judgment. And fundamentally, I think this is because these are probabilistic tools, but we as humans are not probabilistic thinkers. If you've ever been on rounds with physicians or in medical school lectures, we don't think in terms of probabilities. We think of terms of mechanisms and pathophysiology and clinical narratives. And so because of this limitation in our ability to engage in Bayesian thinking, it sets us up for a weakness as far as incorporating information from algorithms to update our thinking. And so this is one of many excellent examples from high-profile literature showing from the past several years that physicians generally exhibit suboptimal performance at updating our reasoning with statistical information about new tests or outcomes. And so this highlights this phenomenon of predictive dissonance, which is the term that I mentioned in the title of this talk, which I think is one of the biggest rate limiting steps in this field of using AI for clinical decision making, which is that when a human predicts one thing or believes one thing, but the algorithm predicts another, we're at a loss for how to fully, accurately, and consistently incorporate that dissonant prediction into our clinical judgment. So what are some options for better collaboration? One proposed strategy is something you may have, I'm sure many people in this room are familiar with, which is explainability. And the logic here is that, these models are very complex, they're black boxes, and so explaining how the algorithm arrived at its prediction might be able to help us better weave its recommendation into our decision making. But unfortunately, what studies around explainability show thus far is that explainability in the way that it's currently done generally does not tend to improve decision making. This is an excellent example of heat maps that are overlaid on chest X-rays that attempt to explain how an algorithm arrives at a diagnosis from a chest X-ray to a radiologist. But it turns out that when the algorithm makes an incorrect prediction, giving the heat map to the radiologist does not mitigate the negative effects of that incorrect prediction. And so ultimately, I think there are two main flaws with how explainability is done thus far. One is that they're often statistical measures themselves that clinicians aren't trained to interpret or respond to. And the second is that in many cases, they're not actually accurate representations of how the algorithm arrived at its prediction. One alternative solution is to go back to the Kasparov's law idea that he first uncovered in 1997, which is to use structured interaction protocols between decision-making algorithms and physicians to ultimately make patient care decisions. And so this is an excellent example from radiology, again, showing that when you give a weaker radiologist, or a less experienced radiologist, I should say, access to an algorithm, and you give more experienced radiologists access to that same algorithm, the weaker radiologists actually tend to outperform the more experienced radiologists depending on what collaboration protocol is used. But I think the boldest and most promising solution as it relates to physician AI collaboration is to actually stop trying to force human intuition to merge with AI predictions, and instead to let AI operate independently on tasks that it's better at, so that physicians can focus our expertise on other areas. And so one radical version of this is what's called role separation. And so this would, take the form of having AI handle certain routine cases independently, like normal chest x-rays or low-risk mammograms, while doctors can focus on the more complex disorders or rare conditions with atypical features. This is an example of an excellent study, again, from radiology, showing that an AI system could very reliably label the vast majority of chest x-rays, of normal chest x-rays given to it, which then freed up radiologists to devote much more time to studying the images that were deemed more suspicious or higher risk. However, this is in contrast to when AI and radiologists were forced to read the same x-rays together, in which case it took twice as long with no improvement in performance. So there's a lot of work that's been done on human AI collaboration, as you've noticed from a lot of the literature I've cited in radiology, but the work that I'm focusing on is around what optimal collaboration for patient care looks like in surgery, both in the operating room and outside the operating room for care of surgical patients. And so I think the bottom line ultimately here is that the capability of these tools for clinical decision-making is very, very rapidly evolving. And that's not really the rate-limiting step. What ultimately the rate-limiting step is that no matter how accurate or how powerful these models get in giving us the right clinical answers, the fundamental interaction challenges still remain. And I think one of those biggest challenges is how we can figure out how to incorporate these recommendations into our clinical judgment. So thank you.
Thank you so much, Jayson, for that talk. We have quite a few questions, so we'll see if we can field them. Again, if you want to ask a question in person, you do so. What's the microphone here? The first question.
Oh, sure. Thank you. Great presentation. I'm wondering if you can speak a little bit to the back end of the training of the algorithm. So the creation of the data, the inferential bases that allow the algorithm to actually outperform the physician. Because there still is a lot of human aid going in the back. And it's when we talk about those metrics, I just think it's not necessarily just a machine outperforming a human. It's more than that. Thank you.
Thank you so much. Yeah, so you bring up an excellent point, which is that which is the issue of what ultimately goes into training many of these algorithms. And I'll mention a couple of points. One is that yes, this very sophisticated algorithms like LLMs have been shown to outperform human clinical judgment, but even simpler algorithms like logistic regression models trained on basic clinical data accessible from the EHR, in many cases are outperform human risk prediction as well. But one subtlety that I think you bring up that's very important is what is the data that goes into these models, and there's a distinction between, I think, information that goes into these models that is objective ground truth versus information that goes into these models that is physician initiated. And so one very, very high profile example was the EPIC sepsis model, which is a AI algorithm that was deployed by the EHR vendor Epic many years ago that tried to detect sepsis in patients before sepsis took effect, so that people can take preventative steps. And when researchers looked under the hood of the model, what they found is that one of the strongest predictors of whether the algorithm detected sepsis or not was whether the provider had ordered antibiotics or not, which basically meant that the algorithm was recruiting the intuition of the physician already in trying to figure out whether whether the patient had sepsis or not. Like it was essentially telling the physician something that they already knew and had already taken action on. And so there is a subtle distinction between how you train these models, whether it's on objective ground truth data versus clinician-initiated data. And models that are trained on objective ground truth data tend to outperform human judgment.
Great, thank you. I think we'll go first next to a pigeonhole question and move on to an in-person question. So one question here with quite a few upvotes is, can you explain how you personally engage with AI in your work as a surgeon?
Yeah, that's an excellent question. So I would say surgery is one amongst specialties is one of the fields that I think has been slow to adopt clinical decision-making algorithms, and in contrast, radiology and pathology are the fastest because they're engaging with imaging data that lends itself easily to inference tasks. I would say that the main ways that I and most surgeons who do use AI on a regular basis is in clinical decision support, preoperatively and postoperatively, when we have things like lab values and comorbidities to use to help inform predictions as to what will ultimately happen to patients after surgery. And that's ultimately the question we all want to have answered is what is going to happen to this patient after surgery, because that helps us inform what operation we do and whether even to operate or not. And so those types of algorithms are what we use kind of most routinely. I would say that AI for real-time decision support, like in the operating room, is not yet something that is broadly used. However, I think there's tremendous potential for this. Again, as I mentioned, I'm a minimally invasive surgery fellow, and so I use robotics in the operating room a lot. And that influx of digital platforms, namely robotics, into the operating room, I think allows, there's tremendous potential for that platform to allow AI algorithms to start entering the operating room and give us advice while we're doing surgery.
So it sounds like at this point, more post-op than real-time.
Pre-op and post-op.
All right, super, thank you. Next question would be in person.
Hi, great talk. Thank you. There's some great ideas. So, as a fellow clinician, one of the things that I think limits clinical adoption, something that we struggle with, is when the AI gets something wrong, it often does it in a way that to humans seems odd or sometimes even inexcusable. And sort of the general example of this, if you will, computer vision would be Tesla autopilot. Everyone's probably seen a video where the autopilot is driving down the road, and all of a sudden, for no reason, it veers off, and now Tesla's upside down in the ditch. And when you review the video, you may see something like a shadow or a branch or something like that to the AI looks like the road was ending, so it would turn. But to a human, it would have been sort of a trivial or kind of silly error almost. I don't have numbers of how good Tesla autopilot is, but I imagine it's 99.9% plus on its accuracy. So when you deal with complex situations with human beings who are sick, you have something that's 92%, even 95, 99%. What do you see as the framework for how that's going to play out? If the AI is wrong, it's in a way that, as a clinician or a surgeon, the error seems kind of odd.
Yeah, that's such an excellent question. I would say, so to kind of emphasize your point, I would say first, you're absolutely right. These algorithms tend to we tend to anthropomorphize these algorithms and come up with, kind of explanations on our own for why they arrive at the predictions they do. But again, these are statistical machines. They are not human thinkers, and therefore the kinds of errors they make will not be ones that resemble the kinds of errors that humans make. So then the question is, how do you mitigate the impact of these wrong answers, and especially when on the aggregate they tend to outperform humans. And I'll be honest with you, I think it ultimately does come down to physician AI interfaces and collaboration protocols. I don't know what the ideal protocol, collaborative interface sort of looks like, but ideally it's one where the algorithm is not so convincing that in 100% of cases it steers the physician towards its answer, but rather one where there's a delicate balance of giving the physician some insight into how it arrived at its prediction so that we can vet whether it's logic in some sense, to anthropomorphize it, whether it's logic or it's, the steps by which it arrived at its prediction. I think giving us some insight into how it arrived at its prediction ultimately will help us figure out whether it's something we should incorporate into our judgment or whether it's not. Thank you.
Okay, thank you so much. I think we're done today for this talk. I really appreciate it. Thank you so much.